Acetaldehyde, aka ethanol, is one of the important raw materials to synthesis substances such as acetic acid, acetate, and more. So there are three main processes to synthesis acetaldehyde in the industry based on our study, which are dehydrogenation of ethanol, oxidation of ethylene, and the partial oxidation of ethanol. So for the dehydrogenation of ethanol, the heated ethanol vapor is passed through a tubular packed reactor consist of the catalyst, which is usually copper, and the pure acetaldehyde is then extracted via alcohol washing and then distillation. And for the oxidation of ethylene, the ethylene and oxygen is passed through a catalyst of metallic palladium and the CuCl2 solution in the reactor. It can be further classified into one-stage and two-stage process. For the two-stage process, it involves alternating of the reduction and oxidation of a catalyst among ethylene and oxygen in the reactor. And for the partial oxidation of ethanol, industry, the pattern process is called verbal chemistry process. The vaporized ethanol is mixed with air and passed through the silver catalyst in reactor typically. So the acetaldehyde and unconverted alcohol are removed from the exit gas by washing with cool alcohol, similar to dehydrogenation. And for the physical properties of the acetaldehyde, basically it's just a colorless liquid at standard condition. It has a pungent and subalkali smell, have a boiling point of 30.16 degrees Celsius at 1 atm, at the melting point of -1 to 3.5 degrees Celsius at the specific volume of 0.531 at the boiling point.
I will continue in explaining the synthesis route. The first synthesis route is the dehydrogenation of ethanol. Dehydrogenation of ethanol. What is dehydrogenation? Dehydrogenation is a process to form a new chemical product by removing hydrogen from an organic compound. But nowadays, the dehydrogenation process involves a presence of a catalyst. It is to increase the number of yield of the products and make the reaction faster. An example of catalyst is copper and chromium. Dehydrogenation of alcohols is the most common method in producing aldehydes and ketones. The formation of aldehydes from dehydrogenation is the elimination of primary alcohols, while the production of ketones is the breakdown of the secondary alcohols. Acetaldehyde is the main product. Therefore, ethanol was chosen in this reaction as it is a primary alcohol. Next is the mechanism of dehydrogenation. Firstly, the dehydrogen will remove from the ethanol as soon as the ethanol reacts with the surface of the catalyst, which is the OMO. Then the ethanol will form an ethoxy after the breakdown occurs upon the surface of the catalyst. Acetaldehyde is formed when the C-alpha H bond cleavage of the surface ethoxy species in the dehydrogenation of ethanol is limited. Lastly, the gas phase of hydrogen formed when there were only two surface-bound hydrogen atoms left on the surface and subsequently dissolved with each other. This is the balanced chemical equations of reaction. And this is the schematic diagram of reaction. Packed bed reactor is the most suitable reactor for this reaction. It is because, firstly, the cost is very cheap in operating and processing. The chemical reaction takes place on the surface of the catalyst, and it produces the highest conversion per weight of the catalyst among the other catalytic reactors. And PBR is also a well-demanded reactor in the chemical reaction practical and industry. Next synthesis is direct oxidation of ethylene. Direct oxidation of ethylene is also known as the Wacker-Hoyce process. It is a process that commonly used in industry to produce acetaldehyde. The Wacker-Hoyce process was developed in the year between 1957 and 1959 by Wacker Chemie and Hoyce. The production of acetaldehyde by direct oxidation of ethylene involves using a catalyst, such as palladium chloride and copper chloride. This is the reaction in Wacker-Hoyce process. There are three equations involved. Okay, first, equation 1, the reaction of ethylene and aqueous palladium, which is the catalyst. The second equation is the process of metallic palladium reoxidized by copper chloride and then regenerated with oxygen. Equation 3, which is the former equation in the direct oxidation of ethylene reaction. This is the schematic diagram of the direct oxidation of ethylene. And the below is the several side products that form from the direct oxidation of ethylene reaction. This is the mechanism of Wacker-Hoyce process. Packed bed reactor, TBR, is also a suitable reactor for this reaction. There is the two synthesis route in producing acetaldehyde. However, we only choose one for the best reaction in producing acetaldehyde, which is dehydrogenation of ethanol. This is the reason why we chose dehydrogenation of ethanol. Firstly, it is low cost in operating. Second, it is high conversion per unit mass of catalyst. Third, the approach uses only use one reactant, which is ethanol, which can be made from more abundant resources. And fourth, the product of this process which is hydrogen, can be employed as a fuel cell energy source.
Hello everyone, my name is Narashikin, and now I will explain about reaction kinetics. So, what are reaction kinetics? Reaction kinetics, also known as chemical kinetics, is a study that analyzes the rates of transformation where the chemical compounds change from reactant species into product. Copper catalysts are chosen as it is the most effective catalyst material in dehydrogenating alcohols. However, pure copper catalyst lost its activity rapidly, so copper bases are added into the reaction. So, we ended up choosing copper chromium oxide mixture as catalyst. But why? This is because by using amphoteric or basic metal oxides as catalyst, an increase in dehydrogenation activity can be achieved. Hence, a copper chromium oxide mixture is added into the reaction to get higher yields. The molar ratio of chromium to copper catalyst is 4 to 40. The table shows the reaction rate constant and the activation energy at different temperatures. From the table, the catalyst gave the highest dehydrogenation energy at the temperature of 582 Kelvin. The graph shows the test for the first order kinetics of catalysts. It is concluded that the reaction operating at T equals to 310 degrees Celsius has a reaction rate constant of K equals to 137.07 dm³ per mole per minute and an activation energy of 11,510 Cal per mole. Next, I will be explaining about the reactor system. The most suitable reactor to be used in this reaction is packet bed catalytic reactor. For PBR, when pressure drop across the reactor and catalyst decay are considered, the integral form of the packet catalyst bed design equation can be applied to calculate the catalyst weight, where W is the weight of the catalyst required to lower the entering molar flow rate of species A and Fa0 to a flow rate Fa. We have a stoichiometric table for the reaction. By only considering the main reaction, let A as ethanol, B as acetaldehyde, and C as hydrogen gas. The value of delta can be calculated from the stoichiometric coefficient, and we get the value equals to 1. To calculate the value of epsilon, Ya0 is multiplied by delta, and we get the answer as 1.
Okay, next I will continue with the multiple reaction part. For this part, we have to list down all the possible reactions that might occur in this reaction. So there are one main reaction and two side reaction. The main reaction is C2H5OH produce CH3CHO, which is aldehyde, and hydrogen gas, which the rate law is K1CA. For the calculation part, question asks to calculate the catalyst weight or the reactor volume in two cases, which case 1 is in isothermal and isobaric. Case 2 is in isothermal and non-isobaric. We are also required to calculate the yield and selectivity for case 1. For the calculation part, we are using an assumption where the side reaction is neglect, and we are only using the main reaction. Before straight away doing the calculation, we list down the reaction condition for this reaction, which mass of aldehyde produced, temperature, initial pressure, and outlet pressure. For the conversion, we choose the maximum value of conversion. From the mass of product value that given in the question, we can calculate the molar flow rate for aldehyde and get 0.4319 mole per minute. Using the formula FB over conversion, we get the Fa0 value, which is 0.4546 mole per minute. And by using the formula Ca0 is equal to Ya0 multiplied with initial pressure over RT, we can get Ca0 is equal to 0.02089 mole per dm³. Delta that we got from this reaction is 1, hence the epsilon is 1. In case 1, we are assumed that the reaction is in isothermal and isobaric. Thus, T initial over T and P over P initial is equal to 1. Then, from the mole balance, we rearrange it using the integration at dx and dw part. Then, the weight of catalyst used for this case that we got is 0.8004 kg. Moving on to the next case, which is non-isobaric, the pressure drop is from 1 atm to 0.8 atm. All the steps same just like case 1, but we just have to include the P over P initial value, which is 0.8. The final answer, which the weight of catalyst used in this case is 1.0005 kg. Selectivity is calculated using this formula, but since from our research has too many possible side reactions that could occur, we assume the selectivity at 0.95, which the experimental value they gained from a research paper. The yield that we got is 95%, which it got when molar flow rate of product formed divided by molar flow rate of key reactant consumed. I also include the MATLAB command. This is for case 1. And this is for case 2. And this is the MATLAB command output for the two cases. That's all from me, thank you.
In conclusion, the objective of designing a reactor producing 10 metric ton per annum of acetaldehyde has been achieved by selecting the process of dehydrogenation of ethanol. The weight of catalyst needed for the isothermal packet reactor is 0.8004 kg for isobaric condition and 1.005 kg for non-isobaric condition, respectively. The catalysts used are chromium and copper mixture compared with the pure copper catalyst, which is typical one. This type of catalyst provide higher selectivity and conversion of acetaldehyde. And these are the list of reference used.